Okay, so today's lesson's on empirical and molecular formulas. Two things that you'll need for this lesson: periodic table and a calculator. So if you don't have those right next to you right now, you should stop the video and go and get them. Okay, so we're going to start off talking about empirical formulas. An empirical formula is a chemical formula, but it's a specific type. It shows the composition of a compound in terms of the smallest whole number ratio of the atoms that are involved in that compound. So if you recall from the naming unit, when we name ionic compounds and we write the chemical formula for them, another name for the chemical formula for an ionic compound is a formula unit. So when you write the formula unit for an ionic compound, we always reduce the subscripts to the lowest possible ratio, or the smallest whole number ratio. And so typically with ionic compounds, the empirical formula is going to be the same as the formula unit. But for molecular compounds, it's a little different. Molecular compounds we don't reduce. If you recall, when you're naming or writing the formulas, molecular compounds use prefixes, and there's no balancing of charges, and so there are times where the molecular formula or the chemical formula for a molecular compound is not always going to be the smallest whole number ratio. And so the empirical formula may or may not indicate the actual numbers present within a molecule. Now here's a table that just gives you examples of a few different types of compounds. And what I want you to notice in this table is if you look first at the ionic compounds, the chemical formula matches the empirical formula, because the chemical formula for ionic compounds is already in its smallest whole number ratio. So in the case of sodium nitrate, in the chemical formula, you have 1 sodium, 1 nitrogen, and 3 oxygen. And so that's a 1:1:3 ratio, which cannot be reduced to anything lower, and so the empirical formula is going to be identical. Now, in the case of covalent compounds, like diboron hexahydride, if you look here, the ratio of boron to hydrogen is 2:6. Well, 2:6 isn't the lowest possible ratio, and so when we put that into an empirical formula, what we do is we reduce the ratio to its simplest whole number ratio, which in the case of diboron hexahydride, its empirical formula does not look identical to its chemical formula. So you can also look down at the bottom at carbon dioxide. Now carbon dioxide, even though it's a molecular compound, its chemical formula is a 1:2 ratio. Well, a 1:2 ratio is the simplest whole number ratio, and so you'll notice that its empirical formula does look identical to its chemical formula. And so in the case of ionic compounds, the chemical formula will match the empirical formula, but in the case of molecular compounds, the chemical formula may or may not match the empirical formula. So what we're going to do today is we're going to learn how to how to find the empirical formula given the percent composition. Now in our previous lesson on percent composition, you learned how to find the percent composition given the molecular or chemical formula. Now what we're going to do today is we're going to learn how to find the empirical formula given the percent composition. Now why this is important is because typically in nature, when you find a compound, you're not going to automatically know the identity of that compound. But you can do some analysis of the compound, and through different types of analysis, you can actually find the percent of each element involved in that compound. And if you know the percent of each element, you can determine its empirical formula, which may or may not be the same as its molecular formula. But because this question's just asking us for the empirical formula, we can do that with the information provided. So diborane gas is 78.1% boron and 21.9% hydrogen. Now, whenever you're given the percent composition, the first thing you want to assume is that you have 100 grams of a sample. And if you have 100 grams of a sample, then the percent is going to be the same as its mass composition. So really, in simple terms, you're going to take the percent and you're going to just change it to grams by simply taking 78.1, and instead of putting percent, you're going to put grams of boron. Now you'll do the same thing for hydrogen, so 21.9 instead of using percent, we're going to use grams of hydrogen. Now, we can see here that boron has a much higher mass than hydrogen. But if you remember, or if you look at your periodic table, you will see that hydrogen is actually much smaller and much lighter than the boron atom. And so what we need to do to actually get a ratio of the number of atoms is we need to convert each of these values into moles. Now, what we're going to do is we're going to multiply each one of these values by the molar mass. And we know that 1 mole of boron, looking at the periodic table, so stop, look at the periodic table, look for boron, and find its atomic mass. Now, when you look at the periodic table, you're going to see that its atomic mass is 10.81 grams of boron. And what we're going to do is we're going to cross out our units there, and we're going to divide 78.1 by 10.81. And if you have your calculator, I recommend you do it to make sure you're getting the same answer. You should end up with an answer of 7.22 moles of boron. Okay? Now you're going to do the same thing for hydrogen, but make sure when you do it for hydrogen, you're not using the mass of boron, you're using the mass of hydrogen. So you're going to need to go back to your periodic table and look up what the mass of 1 mole of hydrogen is. So you look it up and you find that it's 1.01 grams for every mole of hydrogen. And you're going to cancel out those gram units, and you're just going to divide 21.9 by 1.01. And when you get your answer here, you're going to end up with an answer of 21.7 moles of hydrogen. Okay, well remember, when you have moles, because moles are a quantity, now we can actually see or start to see the ratio. Now, a 7.22 to 21.7 mole ratio is not a simple whole number ratio. So now that we've converted both of them to moles, the next step we're going to do is we're going to take the smaller of the two values and we're going to divide everything by that value. Well, out of 7.22 and 21.7, 7.22 is the smaller value, so we're going to divide everything by 7.22. Now, of course, when you take 7.22 and divide by 7.22, you get 1. And so we have 1 mole of boron. And I'm going to do the same thing for hydrogen, 21.7, and divide by 7.22. And when you plug this in your calculator, you're going to get an answer about 3.01. But 3.01 is close enough to 3 that we can assume that it's just 3. So we're going to say for 1 mole of boron, there are 3 moles of hydrogen. Now, this is the simplest whole number ratio for boron and hydrogen for this compound. So we can determine the empirical formula based on that. And remember, when we're writing a formula, we don't use the subscript 1, so we just write the letter B. And then next to that, we write H and how many we have, which is 3. So our empirical formula for diborane gas is going to be BH3. Okay, let's do another example. This time we have 3 different elements, which sometimes people get scared by the fact that there's 3 elements, but we do the exact same thing. So remember, the first thing we're going to do for this problem is we're going to change the percent sign to grams. So 52.1 grams of carbon, and then 17.5 grams of hydrogen, and 30.4 grams of nitrogen. Now again, a gram to gram comparison doesn't give us a very good ratio, so what we need to do is we need to convert each of these values to moles. So I look up at my periodic table, 1 mole of carbon, and you will find that its mass is 12.01 grams. Okay, so we're going to just divide that, and you will get an answer of 4.34 moles of carbon. Okay. Now you're going to do the same thing for hydrogen, and from our previous problem we already did hydrogen, so you shouldn't have to go back to your periodic table. We know that the mass of hydrogen is 1.01 grams, so we cancel out those units, and we can see that the answer is 17.33 moles of hydrogen. And then the last one we'll do is nitrogen. We look at the periodic table to find the mass of nitrogen. and we should see that it's 14.01 grams. And when you calculate that, you get an answer of 2.17 moles of nitrogen. Okay, so again, we now have a mole ratio of carbon to hydrogen to nitrogen, but it's not the smallest whole number ratio. So if you remember, the next step we're going to do is we're going to look at these three values and we're going to see which number is the smallest. And 2.17 is the smallest value, so we're going to take all of these values and we're going to divide by 2.17. So we divide everything by 2.17. And when you divide 4.34 by 2.17, you get 2. When you divide 17.33 divided by 2.17, your calculator will give you 7.99, which is close enough to 8 that we're just going to say that it's 8. And if you round properly, it would round up to 8 anyways. And then 2.17 divided by 2.17, of course, is 1. So given this, now we have simple whole number ratios. And because one of our values is 1, we know that these can't be reduced any further. And so if we write the chemical formula, or the empirical formula in this case, it would be C2H8N. And we don't use the subscript 1, so we would just leave it as N. And this would be the empirical formula. Okay, so now this is a practice problem you're going to do on your own. So make sure that you don't just stare at this question, that you actually take out your calculator, which you already should have out, and take out your notes, write out the work through the problem, and see if you can get the correct answer. Okay, so hopefully the practice problem you did was a breeze because the examples you had were wonderful. But now we want to talk just about molecular formulas as well. So a molecular formula is a chemical formula, but it does show the actual number of atoms in a molecule. And you can determine it if you know the empirical formula of the compound and the molar mass of the compound. You can figure out what the molecular formula is. And the equation you're going to use to do that is you're going to take the molar mass of the compound, which will be given to you in the problem, and you're going to divide it by the mass of the empirical formula. So when you divide these two, what you're going to get is you will get a whole number, which we'll call x. Now what x will tell you is how many times larger the compound is from the empirical formula. And so in order to determine the actual molecular formula, what you'll do is you will take the value x, and multiply it by the empirical formula, which I'm just going to abbreviate EF. Okay, so let's do an example of what that looks like. Now, a compound has an empirical formula of C2H5. That's been determined experimentally. But they also determined experimentally that the molar mass of the compound they're working with was found to be 58 grams per mole. What is the molecular formula? Well, based on the equation I just gave you, we know that the molar mass of the compound is 58 grams per mole. Okay. And what we want to do is we want to find the mass of the empirical formula. Well, we know what the empirical formula is. We know it's C2H5. And so you're going to go to your periodic table and you're going to calculate the molar mass of C2H5. Okay? So we're going to do 2 times the mass of carbon, which is 12.01, plus 5 times the mass of hydrogen, which is 1.01. And what you end up getting is a value of 29.06 grams per mole, we'll say. Okay, well, this is the mass of the empirical formula, so what we're going to do is just move it over here, 29.06 grams per mole. And when you divide these two values, you get a value of 1.99. And again, when we're doing anything experimentally, it's very rare that you're going to get the exact whole number, but 1.99 is close enough to 2 that we can just call it 2. Now this number does not have a unit, so all we're going to do now is we've found our x. Remember that x is the answer when you divide the molar mass by the empirical mass. And so we're going to take that number 2 and we're going to multiply by the empirical formula, which was C2H5. And we don't leave our answer like that because that's not a molecular formula. What we do is we take that number 2 and we multiply each of the subscripts by 2. So we take carbon, its original subscript was 2, but we're going to multiply that by 2 because of our value x. So that would be C4. And then we have H, which original subscript was 5. We're going to multiply that by 2 because of our value x and get C4, H10. And this is the molecular formula. So now, again, we have another practice problem for you. So use the example from the previous slide and have fun.